Good afternoon. We continue last week expression. This session is to complement 2 hours talk by Al Hamidi today. Topic today is based on end of news, air and noise pollution. Page page 455 with the frequency. The frequency of a sound indicates the number of cycles performed in 1 second. Question is f equal to 1 over t. T is the period of 1 full cycle. You see the this is the period t. So the unit for frequency is the hertz. 1 hertz is equal to 1 cycle per second equal to 1 CPS. 1000 hertz is equal to 1 kilohertz. The wavelength lambda is equal to the distance the oscillation have propagated in the time period t. So lambda equal to ct equal to c over f. So for example, determine the wavelength of 125 Hz and 8000 Hz on at 20 degrees C in both metric and English unit. So in this case, 343 is the speed of sound in meter per second. For 1125 in feet per second. And you get 425 feet. Lambda is 2.74 meter. Okay, let's try this exercise. Determine the wavelength of 150 Hz in 7000 Hz tone 20 degrees C. So, okay. So meaning the C is 343 or 11,125. What you need to do is just change the C over F. So C is a constant number over F. Sound pressure level, the sound pressure that are normally measured with sound level cover an extremely large range. In order to handle in a simple fashion, a large measurement range and logarithmic measurement scale is used. There are benefits to using such a scale because the human response to sensation, experience, sound, fragrances, pain correspond to a logarithmic scale to a linear scale. This is page 458. So the sound pressure level then is a logarithmic scale LP defined as LP equal to 10 log P RMS over reference. So in this case, reference is 20 times 10 to the power of 5 or negative 5 Pascal or 20 micropascal. So PRMS is a sound pressure of interest. For example, in this example, given P equal to 1 PA and P equal to 1 voltage, the PRMS is referred to 20 micropascal. The unit for sound pressure level SPL or LP is the decibel. So example 3, determine the sound level pressure level for sound pressure at P equal to 1 Pascal. So in this case, because P here is in Pascal, we no need to do conversion unit. This case, instead of 20 times 10 to the power negative 5, change to 10 to the power of 5. Divide by 2, you get 94 decibel. So increasing the pressure, sound pressure level to 1 at the end, times 10 to the power of 5 Pascal, you get 94 decibel. To use this equation, the unit must be in Pascal. LP is in decibel dB. So the exercise is for you to determine sound pressure level at 5 Pascal and 5 atm. So loudness. A young unspoiled ear can hear pure tone if they have sound pressure level as a function of frequency as listed in the lowest curve in figure 2. 20 Hz tone must have a sound pressure level above 70 decibel higher than a tone at 1000 Hz in order for the same just the tone. The curve also indicated the loudness, a subjective interpretation of the method as sound pure tone. The unit describing loudness are called phone. Sound pressure level is dB. By definition, the phone is equal to sound pressure level in decibels. From 220 micropascal of an equally loud 1000 Hz tone, and pain will occur when the sound is one. An approximate measurement of the loudness of a pure tone can be made by using a sound level meter with a reading record. Most sound level meter equipped with weighing network A, B, and C. The sensitivity of this network is shown in figure 3. So dB is decibel, but if you use any of the frequency with weighing network, it will turn to either dBA, dBB, or dBc. Can refer to page 459. So initially, the intent was that for loudness in the 30 to 60 phone range, the A weighting should be used. Whereas in the 60 to 90 phone range, phone refer to unit loudness. The B weighting applies, and for loudness above 90 phones, C weighting is appropriate. So this is the range needed to use dBA, dBB, dBc. Example, sound pressure level for 100 to 110 is get at 300 meters. For 20 to 30 is the violence. So this is the chart for relative response decibel. Weighing network A, B, and C at different frequency. We have an indoor sound. The acoustical environment in a room depends on the size, shape, and other properties of the confining wall, floor, and ceiling. Before examining how the properties of the room affect the sound field, it is pertinent to examine a simple situation. What happens when a sound source such as a piston is fired out of door in the absence of any nearby reflecting surfaces seen in figure 4? The sound wave arrives at time t equal to R over C, where R is the distance between the source and the receiver, and C is the speed of sound. So the speed of sound is 353 meters. We refer to page 462. So for this case, it's straightforward. There's no wall, so T is equal to R over C. But for the case with the wall, we have two sources of sound which arrive at different time. If there is a large wall or building distant near the firing position as evident in figure 6, figure 5, the receiver will hear a different sound. The first sound wave will be from the direct arrival, R1. Second sound wave from the detected arrival, R2. The two sound wave will arrive at so different time. T1 equal to R1 over C, so this is the distance. For T2 from the wall. The human here is able to recognize individual sound waves if they are separated by a time period of about 50 milliseconds. If the time difference between the direct sound and the reflected sound is greater, an echo will be heard. If the time difference is less, the 1 modified phase will be heard, as evident in the figure 5. Example 4. Determine the time receiver will hear a pistol shot when the distance between the piston and the receiver is 200 meters and there is a building behind the piston. 40 make the calculation for 2 temperature. So for this case, behind the person or receiver, there are wall 40 meters away, meaning when it reflected against the wall, the total R is actually 80. Correct? Yeah, 80. Should be 80 here. I look in the book. In the book is wrong. Should be 80. So C is referred to equation 1. Equation 1 we can refer to earliest slide where we calculate the speed of sound. It's either in Kelvin or in Rankine. In this case, we use Kelvin 20.05. Temperature in Kelvin. So 273 minus 10 gets 263. So the speed of sound at negative 10 is 200 per second. And then you can calculate the time. So for this case, 200 meters directly T1, okay, speed of sound. The receiver will hear the sound in 0.615 seconds. And the second sound, the output, affecting from 40 meters away one is 0.872. And with the increasing temperature, the time taken for the sound to travel is actually reduced. Yeah, yeah, by a lot. The reflected sound wave is weaker than the direct sound wave. For two reasons. This is sound wave. Yeah. It will have traveled further than the direct sound wave. Then the sound intensity decrease with distance. Some sound energy will be lost in the process of reflection. This is the reason why T2 is slower than T1. Do this exercise. In this case, similar collision, but the piston between the zero and the piston is 200 meters, and the building is behind piston is 65 meters away with the temperature is 0 and negative 5 degrees C. So if the piston is in an enclosed space and the receiver is inside the room, he and she will then receive a number of inputs one after the other. In a room, however, the individual inputs tend to blend together because they occur in such rapid succession. The individual inputs are difficult to separate for a second reason too. We can imagine that the reflection are caused by fictitious neural sound source of first, second, and higher order. With the higher order representing successive reflection, the higher the order of the mirror image, the weaker the sound source because source energy will be lost every time the sound wave reflects. This is a sound build up sound decay. Why we need to learn this? Because later on go into noise control. There will be some calculation. The changes in the sound field in enclosed space will reduce sound source system shown in figure 6 on and off. See, in the first half of figure 6, every set result in the available section. Expressed just another way, every step up corresponding to the potential power of the mirror image. The farther away the mirror image, the later the contribution arrive. The individual step on the curve gradually become smaller, yes, and smaller because the mirror image lies farther away and the intensity of the sound wave get reduced at each reflection. A stationary or steady state station represented by the horizontal portion of the curve in figure 6 is rapidly reached here. So So when the sound source is switched off, the sound level will drop off following a similar step function because the condition from the individual mirror image gradually disappear. It reach a steady state. See, the time it takes to switch the stationary station and the time it takes from the moment the sound source is switched off until the sound is really depends roughly on the acoustical properties of the room. Thus, the rise time or the decay time can be utilized to characterize the room acoustically. It should be noted that figure 6 is presented for qualitative purpose and that actual build-up and decay curve may be smoother or quiet, spiky in depth on the content of the room. So there are some derivation. The equation used to determine the acoustical properties are usually developed according to statistical technique. There are several equations exist, each differing slightly as a result of the different statistical assumptions made. However, all equations are based on the energy balance that will always exist. This is all the how they came about this equation. The energy balance is either energy minus absorbed energy equal to any change in energy. So mathematically, the equation RW minus 1 over 4 dc. D is energy density, C is speed of sound, alpha N is the absorption coefficient of the wall. Is here referred to the how big is the area of the wall. The value emitted sound power in watts. V is the volume of the room in meter cube. We have a d over dt. So changes of energy density over time. So statistical technique must be applied to the middle term of the above equation, this equation, that expresses the amount of energy absorbed per unit time per unit time. If we assume that any time if we assume that at any time the sun field is diffused, that the energy intensity is everywhere equal, then during sun will output decay, the solution to equation 16 is as follows. So to find will up this equation, then to d equal to d naught, in this case d naught is the energy intensity once the medium is reached. 1 minus exponent c, c is the speed of sound, a is the total motion in the room, over 4v is the volume of the room. So a here is equal to the phi n as m, which absorption coefficient times the area of the wall. So for the sound decay here, it's actually this equation, minus 1 minus alpha. And for the stationary equilibrium period, A not equal to W. W is the emitted sound power in watts, CA. Then there's a concept of reverberation time. Now we know that the sound will up sound decay with the equation reverberation of time, page 468. What is reverberation? Time t in a room is defined as the time it takes the sound pressure level to SPL to decrease the value 60 dB below its original value. So this is developed by WC Sabin. So at the end, the unit is in Sabin. Yeah. Develop this definition and draft the following formula based on the preceding equation. In metric unit, T equal to 0.160 V is the volume of room over A is the total absorption. Alpha NSN plus 4M. M is the attenuation coefficient. V is the total room volume. So the term 4M is often replaced in unit of dB over 1000. M to highlight its relative influence on sound level for use in equation 20. The value in table 4 must be divided by 4,340 to about 4M in unit of 1 over M. The table 4 I didn't include it here, but this is table 4. The version of 4M in linear term can be found from the value divided by this value divided by 4340. The total absorption A equal to alpha n is n. So alpha is the absorption coefficient. Yeah, absorption coefficient. S is the area of the wall equal to, if we have that, the design need have a different wall elements. So we have several type of ANSN. So A has the unit of meter square Sabin with the unit for S is depend on the unit of S, the meter square of it. So the optimum reverberation time from an estimation of the reverberation time formula, it can be seen that the total absorption in a room can be calculated from measured reverberation time. Optimum value exists for the reverberation time for various functional species. This is some commonplace speech or lecture hall for 100 meter cube. Reverberation time is 0.61. Reverberation time is how long the time take to reduce the surface level by 60 decibel below its original value. Example for bigger space like rooms of 100,000 meter cube. The churches in the house require 1.9 2.2 seconds to reduce the volume below 6, not below 60, by 60 decibel. Energy density 400, page 469. It is important to recognize, however, that changing the reverberation time also affects energy density. The energy density in a room away from the individual sound sources, where the sound is more likely to be diffused, is directly proportional to the reverberation time. D naught to 4W over CA, so W is the sound power, everyone. C is his speed of sound, A is the absorption, total absorption. So A equal to alpha minus N. In this case, D naught is energy density once the big switch. And T equal to 0.16 V volume of the group over total absorption. The equation using the relationship can be determined to be D naught equal to WT over 13.6 V. We see is taken as 340 with the percentage of the speed of sound. Relationship between direct and reflected sound. This formula, you see, clearly shows that the energy density in a room can only be reduced and density by reducing the sound power emitted to the room or by reduction of the reverberation time, the last being equivalent to an increase in the total absorption. To reduce density, is either to increase this or to reduce this or to increase this. Something like that. Relationship between direct and reflected sound, it must mean that the energy density in the steady state situation was D naught equal to 4W over CA. Close to the sound source, however, the energy density will be larger than D naught. D naught is energy density once equilibrium is reached. Here, get the D note. Assuming there's a sound source appeared evenly in all regions, then D equal to W over C for pi R. R is the distance. Remember, between the sound and the sound source, the pistol, the receiver. C is speed of sound. W is watts, energy power, sound power. The ratio of D to D naught become this, where D over D naught equal to E over 16 pi R. E is the total absorption. As long as the ratio is greater than 1, we are in the direct sound hell. This means that DD is dominant when R square R is the distance between the receiver and the sound source less than A over 16 pi R square. This distance R can be used to determine how far away from a machine an operator must be in order to achieve a noise reduction in a room solely through the use of absorption material. So the total energy density in a room is given by D equal to D naught plus DD or W over CA plus W over C 4 pi R square equal to W over C. This is the simplify. The sun pressure level SPL reference to 20 micropascal can be determined by the equation 28 into equation 11 and utilizing equation 8. So you get SPL equal to PWL is on power level dB plus 10 log 1 over 4 pi R squared plus 4 over E, where PWL is 10 log W over W naught. So equation 9. So W is power. Emitted sound power, W. For example, determine the distance R for which the direct energy density is the main contributor in two different rooms. We have room 1 with volume of 100 meter cube. Room 2 with volume of 20,000. The reverberation time. Reverberation is how long it takes to reduce the original value below 60 dB. So for room 1, you calculate the area first. So in this case, 0.16 times V over T, you get, okay, T is 1 second, 0.16, V is the volume, then you get 40 meters per second. So R square equal to 48 over 16 pi less, which is less than 1, then you get R equal to 1 meter. 1 meter. For room 2, because the volume is big and the reverberation time is low, you get the E equal to 100 meters per second. So divided by 16 pi, you get 25.5 meter. So meaning, sorry, R equal to 5. So meaning to make the sound from the receiver to the sound source, and that sound must be below 60 decibel, it require like 5 meters. That is the R. We do this exercise. The volume is similar, but the sound, the time, revolution time is different. Let's see the effect of how much is differ from the example. Go straight to noise reduction material. In this book, you can easily go through the sound outdoor. I just cover sound indoor. Page 471, actually read about sound outdoor. I think this one is probably useful for such as when you drive the highway, there's a barrier, especially near the resident area. You have to create a barrier between the highway and the residential area. For noise reduction, page 473, this material. Reduction of the sound pressure level in a room can often be efficiently accomplished by reducing the sound power emitted by the sound source. Now regarding the project, I need to submit for moderation first. So next week, the latest, by reducing the emitted sound power, both the direct and the output sound will be reduced. However, it is often not appropriate to modify the sound source because modification may have adverse effects such as reduced efficiency, interference with access to the machine. So in this section, we will consider how much noise reduction can be achieved by the use of disruptive material. Let us look at an example where an existing room has a total absorption of A naught if S square meter of absorptive material is installed with an absorption coefficient alpha, then the total absorption after the installation will be A equal to A naught plus alpha S meter square Sabin. However, only the surface exposed to the incident sound determine the absorption. So if the new method cover any of the older material, meaning you layer it, so A equal to A naught plus S alpha minus alpha naught. So there's a still older material there. Where alpha naught is the absorption coefficient for the wall that will be covered with absorptive treatment from equation 19, with intensity of the absorptive sound will be reduced by A equal to 10 log A over A naught dB. For example, determine the noise reduction of the reflected sound that can be obtained in a 20 times 25 times 35 meter cube space where the reverberation time is 4 seconds and the existing ceiling material having an absorption coefficient of 0.25 is exchanged with the material having an absorption coefficient 0.9. So in this case, we determine the volume first, 17,500 meter cube. We calculate the T. From this equation, you get the A naught. So A naught is 700 meters squared. Sabin A equal to A naught plus S alpha minus alpha. So S here refer to the ceiling material. So 25 times 35 meter cube. So meter square should be, yeah. Then 0.9 minus. So the new material have absorption coefficient of 0.9, and the ceiling, existing ceiling is 0.25. 0.9 minus 0.25, so A equal to 1270 meters per second. Okay, so the next reaction equal to 10 log 1270 over 700. So you get 2.6 decibel of reduction. You do this. Change the reverberation time and the space. For the ceiling material, the space is 25 times. In using absorption trail in an attempt to reduce the intensity of the detected sound, it is beneficial to place the material as close to the sound source as possible. Good result often occurs when a noisy machine is placed near a wall covered with active absorption material. Other alternative would be to cover the machine with a barrier furnished with absorptive material. Canopy with absorptive material can be effective if it is suspended close to the machine. This is some of the suggestion how to reduce the sound. The acoustic of a room are not affected by whether the sound is absorbed by a real surface. In this respect, an open window is a very effective sound absorber because it acts as the sink for all of the arriving sound energy. For real surface, the sound energy can either be converted to heat or transmitted as sound wave in the building structure. So sound absorbing material can, on the basis of the physical process involved, be separated into two main groups: the porous absorber and the resonant absorber. So for porous absorber, you can refer to page 475. Porous absorber are complicated structure often manufactured from glass or mineral fibers pressed into board held together by suitable adhesive. In general, though, the acoustical properties of this material depend on the air particle within the material being set to motion when a sound wave strikes the material. Furthermore, this motion resisted by viscous forces near the surface of the fiber result in part of the sound energy being transformed into heat. The porosity of the material is often important. If the porosity is low, then the sunlight will have difficulty penetrating the material, which is, yeah, makes sense. And most of the sun will be reflected from the surface. If the porosity is large, the sunlight will easily penetrate the material and reflected from the surface will be very small. The substantial absorption will be obtained only if the sound wave can penetrate into the material. It's reduced to a great extent before it leaves the material. One valid generalization about porous absorber is that the first maximum of the absorption occurs when the thickness of the porous material equal 1/4 of a wavelength of the incident sound. For example, D equal to lambda over 4. Lambda is the wavelength. So figure 13 shows how the absorption coefficient theoretically should change when the thickness is changed. So this is the absorption coefficient alpha. This is the thickness of the porous material against the frequency. The first maximum on the curve should occur at a frequency having a wavelength equivalent to 4 times the thickness of the material. However, remember that the complexity of this porous material requires that one should only use data that have been obtained experimentally. So at, for example, at 100 frequency, if you have 2.5 cm thickness porous material, the absorption coefficient is only 0.1. The higher the absorption coefficient, the better the sound absorption. So by increasing it up to 10 centimeter, you can actually have 0.4 absorption coefficient. How many? 4? 3 times better than, or 4 times better than 0.1. Then 2.5 cm. If the absorption material is covered with thin plastic film to prevent contamination or spilling, then the absorption will change. The greatest change will take place at higher frequency, but at which the film will be impermeable to sound. Thus decreasing the absorption coefficient, the least change will occur when the film is no thicker than 50 micrometer. So, yeah. Reason we have a resonant absorber, membrane absorber, of resonant. Resonant absorber can be thought to consist of a simple mechanical system containing a mass m and stiffness s. Each resonant absorber will thus possess a frequency at which a sound energy impinging on it will be absorbed. So meaning this surface is actually resonate with the sound. The formula for the resonant frequency of such a system is F naught equal to 1 over 2 pi then stiffness of M in hertz then absorber M Hertz resonator. So when those who do research for sound, they usually opt for M Hertz resonator. So if you the slide will be can download it later Elite. So next week will be about soil pollution.